Welcome dear students to today's online class. Today we discuss the second part of IR spectroscopy, that is about the types of molecular vibrations. In the previous class we have learned that IR spectroscopy, which is otherwise called vibrational spectroscopy, involves vibrational transitions of molecules from lower energy to higher energy. And also that molecular vibrations can be of two types. One is called stretching vibration, where there is change in bond length, and the other is bending vibrations, where there is change in bond angle. Now here we discuss how to predict the number of vibrations possible for a molecule, and also how to predict which vibrations are IR active and which are not. Again, remember, in the previous class we have learned the necessary and sufficient condition for a vibration to be IR active. What is that? Vibration should accompany change in dipole moment. There should be a fluctuating dipole polarity change, so that electromagnetic radiation will interact with the molecule and result in absorption of IR radiation. Now, when we talk about types of vibrations or modes of vibrations, first what we consider is what is called normal modes of vibration. So, what is meant by normal mode of vibration? Vibration in which all atoms are vibrating with the same frequency and passing through the equilibrium position simultaneously. That is the normal kind of vibration. Now, how many vibrations are possible for different molecules? Let us first consider the simplest case, that is a diatomic molecule like HCl, for example. HCl. You know, it has only one bond. So, how many vibrations are possible? How many normal modes of vibrations are possible? It's only one. This bond can, from the mean position, get elongated, come back to mean position, and get contracted, and it continues. That's what's possible. So, only one vibration is possible for such diatomic molecules. And we know that this molecule is polar due to the electronegativity difference. So when there is vibration, you know that this dipole moment, the vector will increase and decrease. That means it will be fluctuating. So it is IR active. So that's very simple. But when we go to polyatomic molecules, we have some formula. First, we consider linear polyatomic molecule. For example, let us take carbon dioxide. You know, carbon dioxide is linear, right? It's a linear molecule. It's triatomic. So the number of vibrations possible for a linear molecule is given by the formula 3n minus 5, where n is the number of atoms in the molecule. So applying it for carbon dioxide, what is n here? There are 3 atoms. So number of vibrations equal 3 into 3 minus 5 equal 9 minus 5 equal 4. So carbon dioxide is showing it will have 4 different types of vibrations. It is depicted here. It's very important. See, we know that there are 2 types of vibrations. That is stretching vibration as well as bending vibration. Now, stretching is again of 2 types. That is symmetric stretching as well as asymmetric stretching. What is it? See, we have shown it pictorially. CO2, we have just shown a single bond. Of course, it's a double bond. We are just trying to explain the vibrations only. Okay, so in symmetric stretching, you can see how it is shown. On the 2 oxygen, you can see the 2 arrows in opposite direction. So what does it indicate? This bond get elongated simultaneously, come back to original position, and then contract, come back to original position. That is one complete cycle of vibration. Okay, that is continuing. So this is called symmetric stretching. But interestingly, this vibration of CO2 is not IR active. Why? Because even though this bond is polar, because of the electronegativity difference, oxygen is delta minus, this is delta plus, there is a dipole bond moment or dipole here, vector is there, and an equal one is to this side also. So what is the net polarity? 0, right? Even if it is elongating in the same direction, in the same manner, the both vector will increase and decrease all the time, they will get cancelled. So there is no change in dipole moment during the symmetric vibration of CO2. So what we can say that symmetric vibration of CO2 is IR inactive. You won't get any IR peak corresponding to this vibration, right? But you may wonder how we got this frequency. See, these are the IR frequency which we can see in the IR spectrum of CO2. You should Google out IR spectrum of carbon dioxide and you watch the spectrum. You can see only 2 peaks. There will be no peak corresponding to this. Then how you got this value? It's interesting. There is another spectroscopy called Raman spectroscopy, which is a complementary tool to IR spectroscopy. And there is a rule called mutual exclusion principle, which says that IR inactive vibrations are Raman active for some reason that you may learn in some other courses. So this is obtained from Raman spectroscopy. Okay, coming to the next one. Again, before that, if you are elaborating, explaining this in detail, like what are the different pictures of the vibrational mode, is like if this is the equilibrium bond length, okay, and suppose we are drawing like this. See, suppose this is the first photograph of CO2. And after it's elongated, it will be like this. But it will cancel, Then come back to the mean position. Then it contract like this. Bond length decreases like this. And it go back to the mean position. See, this will clearly explain how the vibration takes place. And if we show all the bond moments, you can see that they get cancelled in all the conditions. Okay, coming to the next, asymmetric vibration. What is asymmetric stretching? It is that you can see this bond is elongated, this bond is contracted. So when one bond is elongated, the other bond is contracted. In the next step, it will be this is elongated, this is contracted. So it goes like this. This is increasing, get elongated, this is contracting, like this it goes. Okay, what about this vibration? During this vibration, there will be change in dipole moment, of course, and it is IR active, right? So this is IR active. You can see the frequency, nu AS means asymmetric stretching frequency, 2350 centimeter inverse. You can easily compare. See, this is greater than symmetric stretching, as I told you in the previous class. Asymmetric stretching is more difficult. It requires more energy and more frequency. So how this become IR active? You can easily understand. Suppose this is the first position, okay, the equilibrium condition, bond length. Of course here mu is 0. There is no dipole moment. But if it go asymmetric stretching, like this bond get elongated, correct? And this is contracted. What happens? This vector is greater than this and there will be a resultant in this direction, correct? So there is a polarity. In the next point, it come back to the original position, mean position, and then this get elongated and this get contracted. So now you can see that the resultant vector will be in this direction, see? So here it is 0 and here it is positive value to this direction, then 0, then to this direction, fluctuating. So asymmetric stretching vibration is accompanied by change in dipole moment, change in polarity. So it is IR active and this is a frequency. Coming to the next one, bending vibration. Okay, in bending vibration there are two types of vibration, that is in plane and out of plane with regard to CO2. So see, suppose we are keeping CO2 on this plane, right? Okay, CO2 is on this plane. Here it is carbon and these are the two oxygen. Now what is happening in plane bending? You know, in bending vibration what is changing? Bond angle is changing. So what happens is that in the plane itself the two oxygens are moving to one side, and so that carbon will be moving to the other side. Or if I show like this, suppose this is what? Carbon to oxygen, and this is a plane, it is kept. And what is the bond angle? 180 degree. Okay, so suppose the bond angle is increasing, so two oxygens are coming to this direction. Bond angle is increasing, so naturally carbon will be pushed to the front and then come back to mean position, and then bond angle is decreasing. This is the kind of vibration that is bending vibration in plane. Now a very similar bending vibration is out of plane, and it looks very similar. Only difference is that one is confined to the plane and one is out of plane. So how is it? Again, CO2 is kept in this plane, okay, on a table suppose, and the atoms are coming out of the plane. See, this is the bond angle 180 degree, and suppose the bond angle is increasing, that means the oxygen atoms are now going down out of the plane and then comes up like this. Earlier it was like this, correct? Okay, now it is like this. This is the difference. Now you can say that these two vibrations looks alike, okay, and we can call them degenerate vibration. What is degeneration? State of having same energy. That means these two vibrations are having same energy, or they will absorb the same frequency. Okay, what about the IR activity? Is it IR active? Yes, it is. It is IR active, because if you check, you can see that this bending vibration will result in change in dipole moment. So it is IR active, and it absorbs at what frequency? Very low, 667 centimeter inverse. See that this is frequency in wave number. Okay, we may put sometimes like here wave number. Okay, doesn't matter because it's all very common usage, and so this is the value. Look, compare the value between this stretching and bending frequency. This is much lower. As I said in the previous class, bending is easier than stretching, or bending vibration results in a lower frequency absorption, and here it is greater. Just explaining one, suppose CO2 is undergoing bending. How does dipole moment change? You know, it is in this mean position, mu is 0, okay, and but when the because it is just opposite each other, that's why it is cancelling. Suppose it is coming like this. Now it's very clear. See, if it is bending, changing the angle, what happens now? It's very clear. The vector sum, you know, the resultant vector, there will be a resultant vector now in this direction, correct? So there is a polarity now for the molecule. Now when it goes back and then goes up, then the dipole will go in the opposite direction. So there is fluctuating dipole, and it is IR active. So CO2 bending vibration is IR active. So in short, if you look at the IR spectrum of carbon dioxide, you can see two peaks in it, right? So how is IR spectrum plotted? We have seen in the previous class. It is plotted between percentage transmittance against wave number, and you can see two peaks for carbon dioxide like this. Okay, this will be at 667, and this will be the 2350 centimeter inverse, and there will be no peak corresponding to this, as I said earlier. Okay, you may check it out. See, this is more intense. This is, of course, the peak is less intense because of the probability of vibration and many factors related to the intensity of the peaks of a spectral line that is beyond the scope of our discussion. Okay, now we have one more molecule that is a work for you. You should do it. Okay, that's for water. See, the next case is a non-linear molecule. If the molecule is non-linear, we take the example of H2O. You know, it is bend shape. It is not linear, non-linear. In that case, the formula is slightly different, 3n minus 6. So, what is n here? N is again 3 atoms. So, number of vibrations possible for water is 3 into 3 minus 6 equal 3. There are 3 vibrations. So, vibrations are again first into 2, that is stretching, and the other is bending. Okay, and the stretching is again of 2 types here, that is symmetric stretching and asymmetric stretching, and bending here you have only 1. Okay, and let us see the stretching, how we show it. For water, you know, this is the shape of the molecule, bent. So when we show the stretching vibration, see, both bones are getting elongated, come to mean position, get contracted. We are just, let us show this elongation, for example. So when actually it is like these 2 atoms are moving like this, and this is moving like this. That is how the vibration takes place. So you will have for this movement and for this movement a resultant coming like this. So this is how we show. You understand? See, when this bond is elongated, there will be a vector here. For this one, there will be one here, and the set will be like this. And this is a vibration. Okay. And of course, you know, water is polar. Okay. Water is polar because of the bend shape, and it is having dipole moment, and when it is elongated, the resultant vector will be elongated, and you know that there will be change in polarity. The frequency for stretching vibration is found to be quite high for water, 3652 centimeter inverse. Okay, so this value depends on 2 factors, as I said earlier. Frequency is given by 1 by 2 pi c root of k by mu. That is force constant, strength of the bond, as well as mu is the reduced mass. It depends upon the atomic mass. And the next one is asymmetric stretching of water. Okay. What happens when one bond is getting elongated, the other is getting contracted? Suppose this is getting elongated, so we will show like this. This will be going in this direction, okay, and this is getting contracted, so this moved to this direction, and this will be going in this direction, right? So there will be a resultant for this, like we can show it something like this. Okay, so this is the vibration. Of course, you can show various diagrams explaining this vibration like this, as I did earlier. Like if you are showing the symmetric stretching, after you draw this equilibrium position, then you can show the elongated bond length, then you can show the mean position, then you can show the contracted positions like that, where the dipole, resultant dipole will vary. And when you come to this asymmetric stretching, there also it will be good if you draw in detail. If you draw various diagrams, like after you draw the mean position, then one bond is elongated and the other is contracted. Definitely you will have, this is the bond moment, this is the other one. So there will be a resultant somewhere in this direction. And then it comes to the mean position, and in the next step what happens? This bond get elongated and this bone get contracted. Definitely resultant will be now in this direction. So it is fluctuating. That's when the direction is changing. This is a vector quantity. When the direction is changing, that is enough. There is fluctuation. Okay. Now finally, bending vibration of CO2. Sorry, water. We can show, right? Bending vibration, change in the bond angle. So it will be like this. That is, if this is moving to away, increasing the bond angle, naturally the movement of oxygen will be in this direction. And you can write the bending frequency is much lower. It is 1596 centimeter inverse. That's the frequency, because bending is easier than stretching, as you know. Actually, bending vibrations are again of different types, like in plane, out of plane. Also, this is called scissoring. See, this is what's happening for water. Okay, oxygen, 2 hydrogens, and you know there's a normal bond angle, but not 4.5 degree. If it's increasing, it moves like this. Okay, then come back to mean position, then decreasing. Okay, this is actually an in plane kind of bending, and this is the movement of a scissor. So what do you call this? This is called scissoring. Okay, so there are such scissoring, wagging, rocking, and there is another one, twisting. Such different bending vibrations are also there. A kind of molecular dance, you can say. Ion spectroscopy in that respect is very interesting in the molecular level. So that's about various types of vibrations possible for a molecule, how we predict the number of vibration, and how we predict whether it is whether it is IR active or not. Finally, this bending vibration, how it becomes IR active. See, already this is, you know, this molecule is polar. In this direction there is a resultant. When the angle is increasing, it gets flattened a little like this. Naturally, when the angle increases, you know, the resultant will decrease, correct? The resultant vector will decrease. And when it comes to mean position, again the dipole moment is increasing, and then when it angle decreases like this, what happens? When angle decreases, then the resultant will be still higher, correct? So there is change in polarity, change in dipole moment, so bending vibration is clearly IR active. So that's about the types of vibrations in IR spectroscopy. Okay, see you in the next class for rest of IR spectroscopy. Thank you.